I know I really enjoyed those previous talks, and I'm happy to start our next session that is about surrogate markers and evaluation using causal inference methods. So the first speaker that we have is going to be Fenny Ong. Fenny recently defended her dissertation in biostatistics and is now working as a statistician at Johnson & Johnson in Belgium. So Fenny, please take it away.
Can you see my slide?
Yes.
Okay. Yeah. Thank you, Emily, for the introduction and also for having me today in this session. So my presentation will focus on the information theory approach for the evaluation of surrogate endpoints based on causal inference model. First of all, maybe it should be good to say something about the definition. So following the proposal by Biomarker Working Group FDA, surrogate endpoint is defined as an endpoint that is used in clinical trials as a substitute for a direct measure of how a patient feels, functions, or survives. This last statement here actually refers to the definition of clinical or true endpoints, which is considered as the most reliable outcomes in clinical trials or the outcome that matters most to patients. Nevertheless, surrogate endpoints are used mainly to reduce the study duration or sample size, which eventually will reduce the cost of the trial. However, it is also important that surrogate endpoints are supported by a clear mechanistic rationale and clinical data, providing strong evidence that the treatment effect on the surrogate can predict its effect on the true endpoint. And we call such a surrogate validated surrogate endpoints. For more than 3 decades, there has been substantial exploration in statistics concerning the methodology and measures to evaluate surrogate endpoints. But in the presentation, in today's presentation, I will focus on the information theory approach to validate surrogate. And this approach is actually was first introduced by Alonso and Molenberg in 2007. So to set the scene, our method was developed in the context of single trial setting, and the focus of interest will be on the individual causal treatment effects. We also assume that there are 2 treatments compared in the trial, and in particular, we are developing the method in the setting where the true endpoint is binary and the surrogate endpoint is continuous outcome. This type of setting can be found, for example, in many vaccine clinical trials, where the measurement of the immune response can be used to predict vaccines' protective efficacy. However, it's also important to mention that similar approach has actually been developed in other settings as well, such as in the binary-binary, continuous-continuous, and the most recent one in the survival-survival setting. I will use this notation throughout the presentation. So Z for the treatment indicator, which can take 2 values, either 0 for placebo or control and 1 for the treatment. Y for the vector of potential outcomes. TZ and SZ for the potential outcomes for the true and surrogate endpoints under treatment Z. Delta for the vector of individual causal treatment effect, which consist of delta T and delta S, and they are simply the difference between the corresponding potential outcomes. So using this notation, we propose a new definition of surrogate endpoint, which says that S is a good surrogate for T if delta S conveys a substantial amount of information about delta T. So this definition is based on the concept of information theory, which I will discuss in the next slide. Information theory has actually been applied in a variety of fields, but here I will try to illustrate this concept in the communication theory, which was first introduced by Shannon in 1948. So the goal is to reliably and efficiently transmit a message from a sender to a recipient. And in Shannon's theory, to transmit one unit of information means we reduce the recipient's uncertainty by some factor. We can actually compute the average amount of information that we can get, and we call this measure as entropy. So entropy can also be defined as a measure of association or a measure of uncertainty about random variable. And it is also the basis of the mutual information, which quantifies the relationship between two random variables. So essentially, this mutual information quantifies the amount of uncertainty about one variable expected to be removed if another variable becomes known. And based on this understanding, it is then natural to quantify the association between delta T and delta S using the mutual information, and we call this measure as individual causal association or ICA. In order to have a nice interpretation, it is also important to ensure that the value of ICA lies within a unit interval. So we propose this transformation of the mutual information. It's also important to note that ICA is actually generic and model independent, but we need to specify a joint causal inference model for the potential outcomes to estimate this metric. So with that, I will now discuss the causal inference model. In Rubin's model for causal inference, we assume that each individual in a trial has a four-dimensional vector of potential outcomes, denoted here by Y, which consists of the potential outcomes for the true and surrogate endpoints in the control and treatment groups. And for this type of model, there is an inherent fundamental problem of causal inference, where out of four potential outcomes, only two are actually observable depending on the treatment that is received by the individual. And this situation makes the distribution of Y and delta is not fully identifiable. So our causal inference model is defined as this decomposition of the joint distribution of the potential outcomes into the marginal distribution of the true potential outcomes and the conditional density of the surrogate potential outcomes. We assume that YT follows a multinomial distribution with parameters pi ij, which actually consists of four parameters. So there is pi 0, 0, or the so-called never responders. This refers to patients who always harmed by either control or the treatment. There is also pi 1, 1, referring to patients who always benefit from either treatment. Pi 0, 1 and pi 1, 0 for the patients who benefit from one treatment but not from the other. Mind you that we cannot estimate this distribution due to the non-identifiability, and what we can estimate using some commonly assumptions made in the causal inference model are these marginal probabilities. And once we specify the value of pi ij, for example, pi 1, 0, we can then fully estimate or identify this distribution. Meanwhile, the conditional density of Ys given Yt can be modeled using a set of normal distribution with parameters means and variance covariance matrix. And marginally, Ys can be distributed as a mixture of normals with parameters pi ij as its mixing proportion. Once the causal inference model for the joint potential outcomes is established, we can also derive a similar model for the joint distribution of delta T and delta S. And we will use the parameter estimates corresponding to this distribution to estimate our metric ICA. If you notice from the previous model, there are 24 parameters in total to estimate. So 4 parameters of pi ij and 20 parameters of the means and variance covariance matrix. A number of simplifying assumptions can be made to reduce this number of parameters to estimate. So for example, homoscedasticity assumptions is often made when we fit a Gaussian mixture model to avoid infinite likelihood. And with this assumption, we can actually reduce the parameters from 20 to 14 parameters. Another commonly used assumptions is monotonicity, which refer to the situation where the treatment can never be harmful or more harmful than the control. And when monotonicity is assumed, we can fix the value of parameters pi10 to 0 so that we can fully identify the distribution of YT. As I mentioned, the practical use of the ICA is hampered by the non-identifiability, which can also be seen as a structural missing data problem, where half of the information cannot be estimated from the data. And in the case of non-identifiability, the focus of inference should be shifted from point estimators to the so-called uncertainty region or interval. This uncertainty basically consists of two components. So first is the imprecision component due to sampling variability, which can actually be solved by collecting more data. There are also some formal procedures available to handle imprecision. For example, we can use asymptotic standard error, confidence interval, or bootstrap resampling. The second component is ignorance, which is due to the non-identifiability. And mind you that this component cannot be solved by merely collecting more data. In this study, we proposed to handle the ignorance component by using sensitivity analysis, which essentially combines two steps. So the first step is we identify the identifiable and non-identifiable parameters corresponding to the causal inference model. And in the second step, we study the behavior of our metric as the function of the non-identifiable parameters. So essentially, with the sensitivity analysis, we assess the validity of surrogate endpoints across a large set of plausible distribution of potential outcomes. So this slide shows the algorithm that we follow for the sensitivity analysis. So in step 1 and 2, we basically sample the non-identifiable parameters from a uniform distribution. And in the next 3 steps, we identify the identifiable parameters based on the sampled non-identifiable parameters. And then after all parameters are identified, we can calculate the ICA, and we repeat these steps as many times as possible until we obtain a set of ICA values which is compatible with our data. Finally, we can also summarize these ICA values using either frequency distribution or the uncertainty intervals, such as range or symmetric density interval. Range is simply the minimum and maximum values of the ICA obtained from the sensitivity analysis, while the symmetric density interval corresponds to the central part of the frequency distribution of the ICA, which can be calculated based on some quantiles. So to illustrate the implementation of the method, I'm going to use a data set from a randomized control trial comparing risperidone to conventional antipsychotic agents for the treatment of chronic schizophrenia. Actually, this example in this particular data set is a bit special in a sense that any outcome can actually be considered as the surrogate for the other outcome. But here, for the sake of illustration, we assume that the clinical or the true endpoint is the so-called CGI or clinical global impression, which we dichotomize. And the candidate surrogate will be the positive and negative syndrome scale or PANSS. So when we applied our method, we will obtain this set of values for the ICA, which can be summarized using this frequency distribution. It's also important to mention that in this analysis, we take the imprecision component into account by generating 300 bootstrap samples from the original dataset before we conduct the sensitivity analysis. So the result here shows that the association between the individual causal treatment effect on CGI and PANS is rather small, indicating that PANS might not be a very good surrogate for CGI. So to conclude my presentation, our metric of surrogacy ICA is again developed in the context of a single trial setting based on the information theory, and we also used the causal inference model to estimate the metric. It offers a unified and yet general framework for defining and quantifying surrogacy. And the proposed methodology is flexible in terms of incorporating plausible assumptions into the analysis, but of course, this procedure should be done with caution. Finally, this is actually a teamwork, so I would like to acknowledge these people here working on the same project. And also you can refer to these publications for further information. Thank you.
Thank you, Fanny. That was great. Not seeing any immediate questions, go ahead and switch over. And then if there's time at the end, happy to take any questions for either of us. Hopefully you can see my screen.
Yes.
So great. So next, I'll go ahead and give a presentation also talking about another causal inference method for surrogate evaluation. And my name is Emily Roberts. I'm an assistant professor in the Department of Biostatistics at the University of Iowa in the US. And you'll see some similarities with my presentation to Fanny's, but by focusing on a different causal inference method known as principal stratification. So just to consolidate the information, we know that randomized trials are a gold standard for measuring treatment outcomes, treatment effects on some outcome, but oftentimes it can take a long time to measure that outcome. So this is where surrogate endpoints really have a lot of promise. It's some endpoint that we might be able to measure earlier in order to make the trial run more efficiently in some way. So in order to use a surrogate for a future trial, we need to validate it first. So we need to use data from a completed trial to assess if it's a good causal surrogate. And it's generally challenging in order to say whether or not a surrogate is good, which is why you'll see different methods being proposed as different metrics for what it means to be a good surrogate. Like Fanny, I'll also be using the causal inference framework of potential outcomes. So just to introduce my notation, I'll be using S to denote the surrogate outcome, T to denote the true clinical outcome or the long-term outcome, and I'll be using Z to denote the treatment level. So in the case for my potential outcomes or counterfactuals, I'll use this notation with parentheses where S of Z and T of Z refer to the respective endpoints had they have been set to treatment level Z. I'll also be focusing on the case where we have a binary treatment. In this case, we can simply write out the potential outcomes for the true outcomes as T of 0 under placebo and T of 1 under the active treatment. In a standard case where we're interested in assessing the treatment effect, we would tend to just come up with one contrast or one delta. That would be the difference between the two potential outcomes. In this case, we're going to be thinking about a more complex setting since we also want to incorporate the surrogate outcome S. And of course, the first challenge that we'll run into is the fact that we don't actually observe data for all of these potential outcomes. So in reality, for a trial, we only observe the set of S of 0, T of 0, or S of 1, T of 1 for any given individual being assigned to treatment or placebo. The idea is that principal stratification will provide a framework to bring together all of these potential outcomes. So we have S of 0, S of 1, T of 0, T of 1, and put them into a modeling framework along with several causal modeling assumptions in order to say whether or not the surrogate is valid for use in a future trial. In the case that we're going to be looking at, we're going to have continuous outcomes that we'll assume are normally distributed. And the idea of principal stratification is that we will be defining causal effects within strata of individuals. In this case, our strata of individuals or patients within the trial are going to be defined by our potential outcomes, which will be a contrast of the surrogate potential outcomes. So here you'll see this notation delta S represents a contrast or the difference between the surrogate under active treatment and the surrogate under placebo. So this is the conditional piece. These are our strata of individuals for which we'll define our effects. And what we're interested in is the expected value, the difference of T1 minus T0, conditional on this delta S. In the case when we are going to assume a normal distribution for the endpoints, we can write this out in a nice, concise manner. Doing the algebra, you can see that what this equates to is one intercept or one term that does not depend on S, which is going to be called gamma naught, and also a function of this S value. And this will be written in terms of gamma 1, and which will be referred to as our slope. So this will be more clear on the next slide with a graphic, but in general, this is the causal estimand that we're interested in. It's the effect of the treatment conditional on strata of patients defined by the surrogate potential outcomes. And our ultimate goal is to estimate these quantities. As we'll see, these two key gamma quantities actually will tell us whether or not the surrogate is valid. And as we'll see, there's a variety of assumptions that are involved in doing so. So this plot is known as a causal effect predictiveness plot, or a CEP curve, and it demonstrates the quantities that I showed on the previous slide. So here on the x-axis, I have these quantities delta S, which you'll recall is the contrast S1 minus S0, and on the y-axis have the contrast delta T, which is T1 minus T0. The idea here is you can think about individuals as being any one of these dots on the plot, and the idea is that we want to understand how their delta S, or change in the surrogate, is associated with delta T, their change in the true outcome. So if we think about an ideal case, we'll be thinking about this upper right-hand quadrant. If we had some individual who had some positive effect for the treatment on the surrogate, they would have some positive value for delta S. And similarly, for the true outcome, if they have some positive improvement under the active treatment, they would have a positive value of delta T. So we would have individuals following in this quadrant. We can also think about a situation where the treatment had no effect, where delta S and delta T are both equal to 0, and those individuals would be falling right around the origin. So the idea is that we're interested in understanding the expected value of this best fit line, being that the surrogate is good if the trend of the data is that the intercept, or where the data are right around when delta S and delta T fall, is we're going through the origin. That's ideal. And also that there's a positive slope to this line. So that would tell us that if there is a causal effect on the surrogate, that there is also a causal effect on the true outcome. So in thinking about our gamma naught and gamma 1 quantities, we're interested in estimating them, which relates to the intercept and slope of this line. And we're interested in the case when gamma naught is equal to 0 and gamma 1 is positive. That will be our valid surrogate. The challenges that arise are from this causal inference missing data problem, where we don't have data for all of these potential outcomes. And correspondingly, we have some parameters that are going to be non-identified, as Fenny mentioned. So the overall idea of this project is trying to understand how different statistical and trial design pieces can help us. And we'll look at a couple, such as Bayesian methods using imputation and other modeling assumptions. To get into more detail about what this distributional assumption looks like, in the case of cross-sectional data, we would be assuming that our potential outcomes have a multivariate normal distribution. So here I've shown our 4 potential outcomes having some mean and covariance structure. And our quantities that we're interested in, gamma naught and gamma 1, are functions of these model parameters. Some of the model parameters, specifically in the covariance structure, are the ones that are not identified, and we'll take special care in order to figure out how we're going to handle them. So that's the cross-sectional case. Today I'll introduce our work that is thinking about the longitudinal case that is motivated by a diabetes study. So here, this is an example of a study and is available through the NIH NIDDK database that investigated a potential treatment to protect beta cells in new onset type 1 diabetes patients. So type 1 diabetes is an autoimmune disease where the body destroys these beta cells that make insulin. And so the goal of this study was to introduce some immune-related treatments that might stop this destruction of beta cell function. So here are our treatments, which again are Z, are intended to influence parts of the immune system. So we'll refer to these as ATG, GCSF. Have full information here about these, but the idea is that they will do something to the autoimmune system and hopefully stop the destruction of these cells. In the actual trial, there were 3 arms. In the case of this analysis, we'll be combining the data such that individuals who received any treatment are in the active treatment arm, which is 58 people, and compare those to those in the placebo arm, which is 31 people. The primary outcome of our study is a measure of insulin production, which is measured by C-peptide. And importantly, these C-peptide measurements were taken repeatedly over a 1-year time period. They also measured candidate surrogate markers, which were broadly measures of immune response. So the one that we'll be focusing on is a CD4-CD8 ratio, which again are markers related to the immune system. So these were also measured both at baseline and at an earlier time period at 24 weeks. The idea here is that we want to expand our causal modeling to the case where we have repeated measures, and we want to do that by using mixed models. So the idea here is to expand this set of potential outcomes or counterfactual outcomes and allow for an entire vector to represent the repeated measures. Here we propose to do that using mixed models and random effects, and in particular, the use of counterfactual random effects. So here's just an idea of what this looks like. I have a fairly standard mixed model written out for the true outcome in terms of some fixed effects mean structure and then a random intercept that corresponds to T of 0 and T of 1. So this captures the longitudinal nature and correlation of the repeated measures for a given individual. The idea here is that we're proposing to model the joint distribution of the surrogate and the random effects by assuming that they follow a multivariate normal structure and using some of the framework that we showed previously in the cross-sectional case in order to define our quantities for validation. Specifically, we'll be redefining the CEP curve and deriving the gamma naught and gamma 1 quantities with regards to time, now that we are taking into account repeated measures. In the case where we have this random intercept model for our true outcomes, we can write this out analytically still, noting that these gamma naught and gamma 1 parameters are still of interest and that they're still a function of our models from the previous slide. How we actually go about fitting these models and calculating these quantities is by thinking about the complete data likelihood and an idea of using Bayesian method in order to do imputation of this complete data being the full set of potential outcomes. And the idea here is that we use Bayesian methods in an MCMC algorithm to impute missing counterfactual outcomes in order to calculate this multivariate normal distribution parameters and estimate those from our imputed data. Here, I think I'll go ahead and skip to the findings that we had related to the diabetes study. Unfortunately, when we applied our algorithm to the CD4-CD8 marker, we did not find it to be a valid surrogate. In particular, I mentioned one of our key quantities, gamma 1, needs to have a positive value. When we did the estimation, it had a quite wide credible interval, being that we couldn't say decisively whether or not it was positive or not. And so there's a lot of things that we're considering on ways to improve upon this model, both for this data set or in the future to make it more flexible, different ways to use more covariates and consider more assumptions about the model, such as conditional independence that Fanny mentioned as well. So those are a few specific things that we're working on. And overall, of course, there's always chances to do more sensitivity analysis with regards to the non-identified parameters. We've been focusing a lot on what types of prior distributions are used within our Bayesian algorithm, but there's always more work and more ways to make this more flexible and apply to more types of outcomes. And then, of course, what I think is really interesting is thinking about how this principal stratification method compares and contrasts to other methods such as ICA. So always more room for comparison and determining what are the best ways to say whether or not a surrogate is valid. So want to thank some individuals and provide some literature in case you're interested in reading up more. Thank you. So I think that wraps it up for our 30 minutes for the surrogate endpoint validation, and can hand it over to the next.